So, over the last couple of lectures we had seen the various kinds of assignments, data flow and the procedural kinds of assignments. Now, in this lecture we shall be showing you some examples of Verilog module descriptions using mainly the procedural kind of assignment statements. So, by doing that you will be understanding some of the design styles and techniques which are good to use and also some of the implications. If you create the design in certain way, then you are expected to get something, otherwise you will be getting something else. We will be explaining a few such issues. Okay. So, we start with an example of a simple 2 to 1 multiplexer. See, we have seen earlier that we had created the multiplexer design using various behavioral and also structural techniques. We use the instantiation of gates to use or create a multiplexer description. We use the assign statements to define the behavior of a multiplexer. Okay. So, also we use that, you just recall that vector with a variable index on the right hand side, that creates a multiplexer. Various ways we have seen, but here we are using a procedural kind of description that also defines the multiplexer using some kind of an if else statement. So, let us see this. So, in this example we are trying to create a simple 2 to 1 multiplexer where the inputs are in 0 and in 1 and the output is f and the select line is s. So, in 1, in 0 and s are the inputs. So, f is an output which is also reg. See, again I am declaring f as reg because inside this always block this f is appearing on the left hand side. Here in the always block I am giving the condition, the event expression is whenever any of the input changes in 1 or in 0 or s. So, whenever any of the input changes I update my value of f. What I do? If s is true, that means s is 1, then this in 1 will go to f, otherwise if s is 0, in 0 will go to f. Now, see, whenever you describe something using this OR notation like this, normally we are expressing or trying to express a combinational circuit behavior. But of course, there can be exceptions we shall be seeing later, that even if we specify the event expression by naming variables using OR, there are cases where a sequential circuit might be synthesized, but we will try to explain when it happens. Okay? But in the example I have given here, it is a simple case of a combinational circuit that will be generated. So, here a simple 2 to 1 multiplexer will be generated, okay, where this in 0 and in 1 will be the inputs, this s will be the select line because you are checking on s, and f will be the output. This OR keywords combines the variables to form the event expression. Okay. Now, I have a slightly modified version of the same program, where in the earlier one we gave OR. Okay. So, instead of OR we can give commas, same thing. This is just an alternate way of expressing, which may be a little more compact. Instead of writing OR so many times, you can simply separate the variables by commas. Now, this notation is supported in the recent versions of Verilog. So, you can use this. Fine. So, as the third variation, so instead of listing the variables I mentioned, we can put a star. What does the star mean? So, whenever any of the input variable changes, now here my input variables are in 1, in 0 and s. So, whenever any of them changes, this always block gets activated and the block is executed. So, the body of the block is the same. Okay. So, these three versions are equivalent. So, you can see this is perhaps the most compact, and here in many design you may use this because it will make your code shorter. Okay. Fine. Now, let us come to some sequential logic examples. this is an explicit synchronous D type negative edge triggered flip flop, where you are using a clock with a neg edge. So, I mean in this description we are trying to define a D flip flop with a D input, outputs Q and Q bar with a clock. So, D and clock we are declaring as inputs, and both Q and Q bar we are declaring as output edge. Well, of course, we could have done what we saw in the earlier examples, where this Q we can declare as edge and Q bar we can generate by using an assign not of Q. But here we have chose to just assign Q and Q bar both inside the always block. This is also a correct description. So, what we are doing inside this always block at the rate neg edge of the clock. So, whenever there is a negative edge of the clock, we are executing two statements. What we are doing? Whatever is on D, that goes to Q, and whatever is on D bar, that goes to Q bar. This is the logic that defines a D type flip flop, which is negative edge triggered. Okay. So, just again to repeat, we mentioned this in detail earlier, that what is meaning of neg edge. Neg edge means whenever this signal is having a negative going edge. Now, negative going was the meaning I told, either 0 to 1 or 0 to x or z or x or z to 0. Similarly, if you want to have it triggered on the positive edge, you can use pos edge instead of negative edge. And this condition, several conditions you can separate by commas or OR. Okay. Let us take another example. This is a simple 4-bit counter. So, you know what a 4-bit counter is. So, a counter is a digital circuit. Okay. Normally, if we do not specify anything else, we mean it is a binary counter. That means it counts in binary. Suppose it is a 4-bit counter. It can store a value which is 4 bits long, 0000 up to 1111, that means 0 to 15. So, whenever a clock comes, the counter will be counting up 0, 1, 2, 3, 4, and whenever it reaches 15, at the next clock again it will become 0. Okay? That is how a counter works. So, here we are trying to design a counter where we can also reset it from outside by activating a signal RST. Reset means we can reset it to all 0, and it is asynchronous, that means it need not be synchronized with the clock. Whenever the reset is active, immediately I can initialize the counter to 0. So, let us see how the description will be. So, here clock and reset are the inputs, and count, here is the example of 4-bit counter. So, the count value is of 4 bits, which is output, which is also edge, again because count is appearing on the left hand side of the assignments. So, here our event condition says either positive edge of the clock or positive edge of reset. So, if any one of them is true, this event condition is considered to be true. So, you go inside and check first if reset was active. Positive edge means there was a positive edge and reset has become 1. So, you check whether reset is 1, then you make the count value 0, else reset was not active, just a clock came. So, you will have to increment the count by 1. Okay. This is a simple description of a counter with asynchronous reset. But if you do not need asynchronous reset, if you need a synchronous reset, then you drop the second part, just only write pos edge clock, then everything will take place in synchronism with the clock. Okay, here this is a little surprising example. See, first thing is that here we have mentioned in the comment that another sequential logic example, but you look at the description, does it look like a sequential circuit or sequential circuit description? Let us look at it in some detail. This is a module, this is the name of the module, just forget the name for the time being. There are two parameters, current state and flag. Current state is a 2-bit vector 0 1, flag is also a 2-bit quantity which is output, also reg because flag is appearing on the left hand side. Now, let us look at our procedural block. Well, always whenever the current state changes, you do this. So, what is my logic? My logic is case, there is a case statement. So, I check the current state. So, if the current state is either 0 or 1, so in case if there are multiple cases which can result in the same expression, you can separate them by commas like in the example shows. If it is 0 or 1, you set flag to 2. If it is 3, you set flag to 0. Now the question is, why am I calling it a sequential logic? So, it is clearly like a combination logic now, just you try to construct a truth table kind of a thing. Suppose I am listing my current state and the expected value of flag which I am setting. So, according to my description, if my current state is 0, I set flag to 2. If my current state is 1, I set flag to 2 again. If my current state is 3, I set flag to 0. So, it is just like a combination circuit, but there is a catch here. Here we have not specified what will happen if the current state is 2. So, we have not specified the value of the flag. So, what is the meaning? Now, the Verilog simulator or the synthesizer will assume the meaning as follows: if some of the input descriptions are missing in the case statement, like here the value 2 was missing, the interpretation will be if current state is 2, then flag will not change. Because we have not specified the value of flag, the interpretation will be the value of flag will remain what it was in the previous state, which implies that flag will map to a storage element. Means latch. So, you will have to store it just for this purpose. Okay. So, whenever there is an incomplete specification, in order to satisfy the interpretation that the Verilog simulator or the synthesizer assumes, that if it is one of those unspecified condition, the output value will not change. To implement that, the output value has to be stored somewhere in a latch, which implies this becomes a sequential circuit, not a combination circuit anymore. Okay. So, for this example, the variable flag is not assigned a value in all the cases of all the conditions of the case statement. 0, 1, 3 we have specified, but for 2 we have not specified. Because flag is a 2-bit register, so a 2-bit latch will be generated for the flag. This is how it will work, right. Now, you see, I mean, as a designer, I know that if I specify a circuit like this by not specifying all the conditions, case conditions, then the synthesizer will be generating a latch. Well, although I do not want this to be a sequential circuit. So, how can I modify it? I can make a small change in my description, like I can just add one line here, remaining part is identical, just one line here before the case. Before the case I add one line. Now, there are two statements, that is why I have given a begin end flag 0. So, now what is the difference? Now, the synthesizer or the simulator, if it does a data flow analysis, it will find that well, for 0 and 1 flag is 2, for 3 flag is 0, but for the condition 2 also flag will be 0, because we have already initialized flag to 0 and have entered. So, if I do not specify, flag will remain at 0. So, now if we look at this truth table we had constructed earlier, now for this case instead of a question mark here, this value will also become 0. So, this will be a pure combinational circuit and there will be no latches that will be generated. So, as a designer it will be your responsibility to write these specifications in such a way that latch is not generated unnecessarily unless you explicitly wants it to be generated. Okay? Fine. Okay. So, here as I said, by doing this the variable flag is getting defined for all possible values of current state, which implies that a pure combinational circuit will be generated by the synthesis tool and the latch as in the previous example will be avoided. Okay. So, to summarize our observation, whatever we saw, that when you use a case statement in a Verilog description and the case statement is incompletely specified, that means all conditions are not given, then the synthesis tool will generate a latch to hold the output values, because whenever one of those means unspecified values are coming, so the synthesis tool will try to keep the output in the previous state, and for that it needs it to store it in a latch. Now, as I said, it will be up to the designer finally to code it in such a way that latch can be avoided, because if you specify your design in such a way that it is incompletely specified, the synthesis tool will assume that as a designer you are wanting to create a latch and a latch will be created. Well, let us take a very simple example to basically consolidate this observation once more. Let us take a very simple example. Suppose we are creating a module description, let us say the name of the module is XYZ. Well, another thing I am specifying here, see the input and output description you can specify here also. The modern versions of Verilog supports this. So, you can specify it like this. Module XYZ. So, means earlier you had mentioned A, B, C, F and this input and output would mention later, but you can specify in the same line also. When you are declaring, you can say input A, B, C, output reg F. This is also allowed. Now, my module description goes like this. Always whenever any variable changes star. So, inside the always block there is a single statement, it says if A is equal to 1, F equal to B and C. This is bitwise AND module. Simple. This is a simple specification. So, here we are saying whenever some input is changing, you check if A is 1. So, if A is 1, you assign B and C to F. Now, you see here I have not used a case statement, but there is a conditional if else kind of thing. So, the situation is very similar. Here also we are not specifying the value to be assigned to F for all possible values of A. We say that if A equal to 1 you do this, but what will happen if A equal to 0? I have not specified. So, if A equal to 0, the interpretation will be the value of F will not change, that means you need a latch. So, the inference is that for the condition A equal to 0, value of F is unspecified. So, what will happen for that? So, if you give this description to a synthesis tool, so possibly your synthesis tool will be generating a circuit like this. It will be generating an AND gate whose inputs will be B and C, then it will be generating a latch where this will go to the D input and the input A will go to the enable input and the output Q will be your F. You see, this exactly models this behavior what you have given. If A equal to 1, so whenever A equal to 1, this enable will be active and BC will be stored in the latch and that will be available on F. But if A equal to 0, which means you are not enabling the latch, so your previous value stored in the latch will remain in F. Okay? This is what you wanted. Now, let us look at a slightly modified version of the description. So, we are using the same example, same parameters, output reg f. Now, here there will be two statements, that is why I am giving a always at the rate star. Now, here there was one statement, no begin end was required, but here I am giving a begin end. So, what I do? I add a statement, let us say f equal to c. Suppose my description is like this, f equal to c and then something like this. If a equal to 1, f equal to b and c, end and end module. So, if my description is like this, then what is the interpretation? Then you see my description says if A is 1, then f will get the value of b and c, and for a equal to 0 I have already initialized f to some value. So, this will be the value when f is 0. So, I have defined now f for both conditions, sorry, for a equal to 0. For a equal to 0, this will be condition, for a equal to 1, this will be the condition. So, now I have specified the value of the output f for all values of a. So, now if you give this description to the synthesis tool will be possibly generating a circuit like this. To generate B C, there will be an AND gate, then it will be synthesizing a multiplexer, a 2 to 1 multiplexer, where the other input of the multiplexer will be C, this will be your input 0, input 1 and your select line will be A, the output will be F. So, see what is happening here? You are saying when A equal to 0, C should go to F. So, if A equal to 0, C will be selected, and if A is 1, this will be selected, B C will be selected, B C will go to F. So, this is a purely combinational circuit, you see. So, this is something which is up to the designer. So, you will have to design it in a proper way, so that the synthesis tool should not get confused and generate a latch, where what you actually wanted is a combinational circuit, right. So, it is greatly up to the designer to specify how you are wanting to guide the synthesis tool. So, you should not mislead the synthesis tool in believing that what you are specifying is actually a sequential circuit when it was not. Okay? Fine. So, let us take some more examples. So, here we have a very simple 4-bit arithmetic logic unit, where the parameters are f, a, b and op, where op specifies, these are 2-bit, it specifies one of 4 operations and a, b are 8-bit inputs. this f is also a 8 bit output which is of type reg, because f is on the left hand side. Well, using parameter command you can specify some constants. I gave some example earlier, like here suppose we are supporting 4 operations: addition, subtraction, multiplication and division. Now, to make our program more readable, we have specified them as add, sub, mul and div, where add means this op is 0 0, sub means 0 1, mul is 1 0, div is 1 1. And here we have an always block, where you are saying whenever it is star, that means any of the input changes depending on the value of op. Well, instead of writing 0 0 0 and 1 0 1 1, I straight away am writing add, sub, mul, div. So, it becomes much easier to understand the code. So, the operation is given directly. Okay. So, this is a very simple way to specify an ALU in a behavioral fashion, right. Fine. This is another example of a priority encoder. This priority encoder has 8 inputs and it has 3 outputs. So, what is a priority encoder? So, a priority encoder, the example that I have said, there are 8 inputs. And there are 3 outputs, and the inputs are given some index values 0, 1, 2, 3, 4, 5, 6, 7. Now, I am assuming that the priority increases in this fashion. My input 0 has a higher priority than input 7. Now, the idea is that suppose I set the input number 2 to 1 and the others are all zeros, then the binary equivalent of 2, which is 0 and 0, should appear in the output. Now, let us take an example where any 2 of them are 1. Let us say this input 1 is also 1, input 4 is also 1, the others are zeros. So, if more than one of the inputs are at 1, then according to the priority you choose the one which has highest priority, that is 1. So, binary equivalent of 1 0 0 1, this should be in the output. So, this is how a priority encoder works. So, let us see the description. So, the input is an 8 bit vector, this is the output, code is a 3 bit vector of reg because it appears on the left hand side. So, again in the always block, whenever there is a change in, there is a begin with a nested if. If in 0 means in 0 is true, which means in 0 is equal to 1. If in 0, code equal to 0 0 0, else if in 1, code is 0 0 1, simple. If in 7, 1 1 1, and if none of them are active, else I am initializing the code then to XXX. You see, the order in which I have checked the bits, that will define the priority. So, if both your in 1 and in 4 are active, but I will get a match in 1 first. So, code will become 0 0 1. This is how priority is determined, the order in which I check the bits, right. So, as I said, the input bits are checked sequentially. So, in 0 will be having the highest priority, and if more than one inputs are active, the first input that is checked will be encoded. Okay. Let us take another example which is also quite common, BCD to 7-segment decoder. Now, BCD, you know, BCD is a way of encoding decimal numbers. Decimal digits are 0 to 9, they can be coded in 4 bits 0 0 0 0 up to 1 0 0 1, that is 9. Okay. Now, 7-segment display looks like this, where there are means either LEDs or LCDs, whatever, there are 7 segments A, B, C, D, E, F, G in that order, and depending on what you want to display, you can glow some of the segments and you can switch off some of the segments. So, in this example, so we are representing the 7 bit as a 7 bit vector in this order. So, A is the most significant bit and G is the least significant bit. And another assumption we are making, that a segment glows whenever the corresponding bit is 0, and when the corresponding bit is 1, the segment will be off. So, the description is very simple. So, input to this circuit will be a 4 bit BCD number, a digit 0 to 3 4 bit, and output will be this 7 bit vector 0 to 6, we call it seg. So, always whenever this BCD changes, I have a case statement. If it is 0, 0 means I have to glow all except G. So, G should be 1, all others should be 0. You see, G is 1, all others are 0. Similarly, for 1, B and C will glow. So, you see only B and C are 0. For 2, 2 will be like this. So, C and F will be switched off, C and F are switched off, like this you can check. So, all these digits are glowing, and the default is you are switching off all these segments. If it is input is something other than 0 to 9, because in 4 bits you can specify any number from 0 to 15. So, if either 10, 11, 12, 13, 14, 15 comes, you switch off all the segments, right. So, there is another simple example of an n bit comparator. This is a pure behavioral description, where A and B are the numbers and the outputs are less than, greater than or equal to. Here again I am using a parameter where I am defining a variable what size to be 16. So, A and B I am defining to be 0 up to what size minus 1. So, for 16 it will be 15 to 0, and LT, GT, EQ are is out. Actually, this will be output range. Let me just correct it. This will be output range. Fine. So, here again in the always I put a start if any of the input changes. So, I start by initializing GT, LT and EQ to zeros. It is very simple. I am making a comparison like this. A and B are numbers, okay. Say for 16, these are 16 bit numbers. I am making a comparison. If A is greater than B, I set GT to 1, else if A is less than B, I set less than LT to 1, else they are equal, EQ equal to 1. Okay. So, it is simple. Now, in actual synthesis, actually we normally do not design a comparator in this way, we shall see later. We typically use a structured design using by instantiating some smaller comparator modules. Now, another means example I am showing here just to show another style of specifying. This is a simpler 2 bit comparator. So, there are two numbers, one is A0 A1, other is B0 B1, and the outputs as usual are less than, greater than, equal to. So, A0 A1, B1 B0, these are all inputs and these three are the outputs. Now, we check always whenever one of the input changes. So, I am writing like this some assignments, this LT equal to, you see A1 and A0, these 2 bits make the first number. So, I use the concatenation operation to define the first number. So, there will be a curly bracket here, let me correct this, there will be a curly bracket, yes. So, A1 A0 concatenation and B1 B0 concatenation. If A1 A0 is less than this, so again I think I missed some brackets here, let me just, yeah, I have just changed the brackets, yeah. If A1 A0 is less than B1 B0, if this condition is true, which means true means 1, so that 1 will be assigned to LT. If this is greater than B1 B0, if this condition is true means 1, that 1 will be assigned to GT, and this equality again if it is true, that 1 will be assigned to EQ. See, here we are exploiting the fact that for logical comparisons relational operators, true is represented by 1 and false is represented by 0. So, we are directly storing the result of the comparison in the target variable indicating less than, greater than or equal to. Fine. So, as the last example, we take a slightly more complex ALU example. You see here we are considering an ALU with two inputs A, B, which are 7 bits. There is an operation which is 3 bits and enable which is 1 bit, and in the ALU out there is the output of the ALU 8 bits, and the output will be stored in another register, we call it ALU reg. Now, this output will be generated in ALU reg and it will be stored in here. So, you see this ALU out, we are just doing a continuous assignment. If enable equal to 1, then ALU reg will be transferred to ALU out, otherwise it will be tri-state Z 4Z. And here description is very simple. Whenever any of the input changes on case operation, let us say 000 means add, then ALU reg equal to A plus B. Suppose 001 means subtract A minus B. Suppose 011 means logical not, ALU reg equal to bit by not, and if it is any one of the others, so in case I can mention default, then I initialize ALU reg to 0. So, this example illustrates the combination of assign and case in always block and so on. This also generates a combinational circuit. So, with this we come to the end of this lecture. In this lecture we have looked at a number of different examples, various ways of using the procedural style of coding, the always block, the different ways of using always block and so on. And we shall be continuing these discussions later and look at more complex and more elaborate structures using which we can model particularly the sequential circuits and finite state machines. Till then, we will have to wait for the next lectures. Thank you.